Today we're going to discuss algebraically closed fields and the operation of algebraic closure. But to begin with, we will discuss two constructions of fields. Let R be a commutative ring with 1 and without divisors of 0. So such rings are also called domains. And we define the field of fractions of R as the set of equivalence classes of fractions. So here, this set is the set of equivalence classes of fractions A over B, where A and B belong to R and B is not equal to 0. And the equivalence relation, well, it's the same as we use in rational numbers. So we say the fractions A over B and C over D are equivalent if and only if AD minus BC is equal to 0. It's an easy exercise to show that this set of fractions is indeed a field. And we also note that the ring R embeds into its field of fractions just by sending element A to the fraction A over 1. Let's consider an example. So this will be the case of functions on affine algebraic varieties. So here, let us consider I to be a prime ideal in the polynomial ring in n variables, say over complex numbers. We consider R to be the quotient ring. So we take the ring of polynomials and quotient by I. Since I is a prime ideal, so this is a domain. This will not have divisors of 0. Geometrically, this describes the following situation. So consider the set X in the affine space, n-dimensional affine space, that consists of points in the affine space, such that for every f in the ideal, f evaluated at this point is equal to 0. Here we interpret the ideal I as a system of polynomial equations, and then X is the set of solutions of this system of polynomial equations. Such sets X are called affine algebraic varieties. And the fact that I is prime, so this geometrically is equivalent that X is irreducible. From this geometric point of view, R is the ring of polynomial functions on this algebraic variety. And if we take the field of fractions, so this will be the field of rational functions. On X. So that is, these are quotients of two polynomials. So if we take R to be C of t, So then we can think that here we take I to be a zero ideal in this ring of polynomials. So here X is the affine line A1. So this is one-dimensional affine space. And the ring of polynomials is the ring of polynomial functions on a affine line. And then if we take the field of fractions, so this is denoted as C of t in round brackets. So these are rational functions. So this is the set of equivalence classes of functions f of t over g of t, where f and g are polynomial functions, and g is not equal to 0. Our second construction is the following. Again, let R be a domain. An ideal M in R is called maximal if, first of all, M is not equal to the whole ring R, and secondly, so if M sits in the ideal N sits in R, then either N is equal to M or N is equal to R. So that is for maximal ideals, we are not able to sandwich a larger ideal between M and R. And we have the following theorem. If M is a maximal ideal in a domain R, then the quotient R quotient by M is a field. So proof. So we need to show that any non-zero element in the quotient ring has a multiplicative inverse. Now, we take a non-zero element in the quotient ring. So this will be A plus M, where A does not belong to this maximal ideal. Consider a new ideal N generated by M together with A. Since A does not belong to M, then N is strictly greater than M. And since M is maximal, this implies that this new ideal N is equal to the whole ring. This tells us that 1 belongs to the ideal N. And so we can write 1 as a multiple of A plus something from the ideal M. So here B belongs to R, and M is an element of the maximal ideal. But then this tells us that A plus M times B plus M is equal to 1 plus M. And this tells us that A plus M has an inverse in the quotient ring. As an example, let us consider again R to be polynomial functions on affine algebraic variety over complex numbers by Hilbert's Nullstellensatz, we have a correspondence between maximal ideals in R and points on the affine algebraic variety. So if we have a point on X, then MP will be functions on X that vanish at P, and then the quotient R by MP is going to be isomorphic to the field of complex numbers, and the projection map from R to this quotient, so this is evaluation at P. We take a polynomial function and compute its value at the point P. So this will create for us a map from the ring of polynomial functions to the field of complex numbers. And this evaluation map is the projection to the quotient by maximal ideal. We state the following theorem. Let J be an ideal in a domain R. Then J is contained in a maximal ideal M in R. The proof of this theorem is based on Zorn's lemma, which is a foundational result in set theory. And Zorn's lemma says the following. Let A be a partially ordered set such that every chain in A has an upper bound in A. Then A has a maximal element. Let us explain the notions that appear in Zorn's lemma. So what is a partially ordered set? So this is a set together with the relation less or equal to with the following properties. It's transitive, so this means that if x is less or equal to y and y is less or equal to z, then this implies that x is less or equal to z. And the second property is that if x is less or equal to y and y is less or equal to x, this happens if and only if x is equal to y. Then a chain in a partially ordered set is just a sequence x1, which is less or equal to x2, less or equal to x3, and so on. So we have a countable linearly ordered sequence. An upper bound of a chain is an element y in A, such that for all j, xj is less or equal to y. And finally, the maximal element z in A is an element with the property that if z is less or equal to x, then this implies that z is equal to x. In general, maximal element in a set A is not unique and need not exist. And Zorn's lemma says that maximal elements exist provided that we have this condition that every chain in A has an upper bound. So, for example, if we take as our set A the set of natural numbers with a natural relation less or equal to, then in this set we will not have a maximal element. And this ordering on the set of natural numbers will not satisfy the condition that every chain has an upper bound. On the other hand, if we take A to be the set of negative numbers with the same relation less or equal to, then here we will have that every chain in the set will have an upper bound, and then the set contains a maximal element, well, which will be -1 in this case. To prove the theorem on existence of maximal ideals, we consider the following set. So consider the set A of ideals n in the ring R such that J is contained inside this ideal n, and n is not equal to R. This set is partially ordered by inclusion. So we say that n1 is less or equal to n2 if and only if n1 is contained inside n2. To apply Zorn's lemma, we have to show that every chain has an upper bound. So let us take a chain. So n1 sits inside n2, which sits inside n3, and so on. To construct the upper bound, P, we just take the union, so k from 1 to infinity, of these ideals nk. It's easy to see that P is an ideal in our ring. Obviously, J is contained inside P, and the only thing that we need to show is that this ideal is not equal to the whole ring. But this is based on the following simple observation. So n, an ideal n, is not equal to R if and only if n does not contain element 1. And since we have that for all k, 1 is not an element of nk, so this tells us that 1 is not an element of the union P. And so P is a proper ideal, and then it belongs to the set A, and it will be clearly the upper bound for this chain of ideals. So now, by Zorn's lemma, the set A has a maximal element M, which will be a maximal ideal in R containing J. Next, let us discuss algebraically closed fields. We begin with the definition. A field F is called algebraically closed if every polynomial f in the ring of polynomials over f of degree n greater or equal to 1 has a root in the field f. So that is, there exists an alpha in f such that f evaluated at alpha is equal to 0. Equivalently, we can say that any polynomial factors into linear factors. So this means that f of x can be written as, well, the leading coefficient times x minus alpha 1 times x minus alpha 2 times x minus alpha n, where alpha j's are all elements of the field. These two properties are equivalent because in the ring of polynomials we have division with remainder. And so if we have a root alpha of a polynomial f, then we can divide this polynomial f by a linear factor x minus alpha. And then by induction, we conclude that this polynomial f will then factor into a product of n linear factors. As examples, we can see that the field Q of rational numbers is not algebraically closed. Here we can consider polynomial x squared minus 2, and since root of 2 is not a rational number, we conclude that this polynomial does not have a root in the field of rational numbers. On the other hand, if we take the field of complex numbers, this field is algebraically closed. And this important theorem that the field of complex numbers is algebraically closed is usually proved in the course on complex analysis. As our third example, let us consider the field of rational functions, C of t. So this field is not algebraically closed. So it's easy to see that the polynomial x squared minus t has no roots in rational functions, because a root will be a function square root of t, which is not rational. Here we give a definition. A field extension f contained in E is called the algebraic closure of f if two conditions hold. One, E is algebraic over f, and two, E is algebraically closed. And the notation here is that E is the closure of f. As examples, we see that the algebraic closure of the field of real numbers is the field of complex numbers. So we see that C is algebraically closed, and this extension has a degree 2, and thus is algebraic. The algebraic closure of the field of rational numbers is not equal to C. So in fact, Q bar is the field of algebraic numbers. So this means that Q bar is the set of alpha in C such that alpha is algebraic over Q. These are complex numbers that are roots of polynomials with rational coefficients. So here, square root of 2 will belong to this algebraic closure, but E and pi are transcendental numbers, so they do not belong to the algebraic closure of Q. Since the number of polynomials with rational coefficients is countable, so the number of roots of these polynomials is also countable. And so we see that the algebraic closure of the field of rational numbers is a countable field, whereas the field of complex numbers is uncountable. So this equality cannot be possible. Our main theorem that we want to prove today is that every field has an algebraic closure. The algebraic idea for the proof of this theorem is very simple. So we need to take this field and we need to add to it the roots of all polynomials. If we have a single polynomial, this is easy to do. So if we have a polynomial f in f of x and we want to adjoin roots of this polynomial to f, then it is sufficient to consider f to be irreducible. And then we can construct an extension, which is f of x quotient by ideal generated by f. And so this will be a field which will contain a root of this irreducible polynomial. So locally, there is no problem of adjoining roots of polynomials to a given field. The problem is to glue all these extensions together. And these problems become set theoretic. So if we look at the field f, so for example, these rational functions in T, the number of irreducible polynomials over this field is huge. And the main difficulty here is assembling all these field extensions into one big set. So the main challenge in constructing the algebraic closure of this field will be set theoretic. We need to construct this one big set that contains the roots of all irreducible polynomials over C of t. As the first step in the construction of algebraic closure, we make the following claim. There exists a field extension K of the field f such that every irreducible polynomial f in the ring of polynomials f of x has a root alpha in K. Let S be the set of irreducible polynomials in f of x. To construct the field K, we start with a ring. So let R be the ring of polynomials over f in infinitely many variables. And these variables, yf, will be indexed by irreducible polynomials. In this ring, we consider an ideal, I, which is generated by f of yf, where f runs over S. Here we claim that this ideal is proper. So this means that I is not equal to R. So we prove this by contradiction. If 1 belongs to this ideal I, then this tells us that 1 can be written as the sum I goes from 1 to n, fi of y fi times some polynomials gi. But we know that we can construct a field extension of f where a given irreducible polynomial has a root. Iterating this construction, we can construct a field extension E of a field f such that these n polynomials, so f1 through fn, have roots alpha 1 through alpha n in E. So then we just evaluate variables y fi at alpha I, where I goes from 1 to n. And then this will read that 1 is equal to the sum I goes from 1 to n fi of alpha I times gi, and that is equal to 0, which gives us a contradiction. And the conclusion is that this ideal is proper, so 1 cannot belong to this ideal. Next, we let M be a maximal ideal in R containing I. So we proved that such a maximal ideal exists. And then we set K to be the quotient of R by the maximal ideal. This is going to be our field K. So consider a canonical projection pi from R to the field K. So then what we get is pi of YF is a root in K of irreducible polynomial f in f of x. So we see that in this field K, every polynomial which is irreducible in f of x has a root. So we see that this field K is generated by elements pi of YF, which are algebraic over F, which implies that K itself is algebraic over F. Now let us iterate this construction. So we set K to be equal to K1, and we define Kn plus 1 as an algebraic extension of Kn such that every irreducible polynomial in Kn of x has a root in Kn plus 1. So then we have this chain of extensions. F is contained in K1, contained in K2, and so on. And so we set E to be the union, j goes from 1 to infinity, of all these extensions. Since each of these extensions is algebraic over the previous one, they are all algebraic over F. So we conclude that E is algebraic over F. And secondly, we know that every polynomial f in E of x has a root in E. This can be explained in the following way. Since E is the union of these fields, every polynomial in E of x, in fact, is a polynomial in Kn of x for some n. And then we can consider an irreducible factor of this polynomial. And we see that this irreducible factor, f, has a root in Kn plus 1, which sits inside E. So this proves that every polynomial in E of x has a root in the same field. And these two conditions together show that E is the algebraic closure of the field F. And we were able to prove that every field has an algebraic closure.